At the end of the last video, we saw an example problem in which the system had no solution. That raises two questions. If we have a linear system or a system of linear equations, one thing we might be interested in is whether or not the solution is or the system is consistent. Or in other words, does it have at least one solution? And then we might also be interested in this question. If a solution exists, is it the only solution? Or in other words, is that solution unique? Well, remember what we talked about last time. I told you that this was a fact, and we're going to verify this when we discuss the material in section 1.2. It's a fact that a system of linear equations will either have no solution, which would make it an inconsistent system, or one solution, or infinitely many solutions. It never has like 5 solutions. It's either one or infinitely many or none. Those are the possibilities. And that is suggested by our intuition and experience with solving things like systems of 2 linear equations and 2 unknowns. The lines can cross at one point or at infinitely many points, or maybe the lines are parallel and they don't cross at all. It turns out that's true when you're working with n variables, just like it's true when you're working with 2 variables. Now, last time we were practicing with our elementary row operations. We know that we can replace a row by that row plus a constant times a different row. We can interchange 2 rows in an augmented matrix that corresponds to a particular linear system, or we can take any row and multiply it by a constant. Now, those are all row operations that are equivalent to operations on the equations. So if I'm taking a row and I'm multiplying it by a constant and I'm adding it to another row, that's the same as taking an equation, multiplying it by constant, and then adding it to the other equation, and then replacing this equation, replacing r sub I, or the equation corresponding to that row, with the equation corresponding to that combination. We practiced that with this example right here. We replaced, or we switched the first and second equation, which was the same as switching the first and second row. Then we took the third row and we replaced it by the third row plus 3 times the first row in order to get rid of that x. We ended up here. And then we saw we had a negative 2y and a y. To get rid of that y, we took this equation, we multiplied it by 2, and we added it to that equation, and we ended up with this statement that 0 is not equal to 2. Notice that when we did the same thing, or the corresponding thing, on the augmented matrices, we ended up right here. Now, this is characteristic of an inconsistent system. This is saying that 0 times x plus 0 times y plus 0 times z equals 2, which of course is not possible. So if you see a bunch of zeros here and then you have something non-zero in that very last column, you know that that is never true, and that means the system of equations has no solution. And remember, we're talking about creating equivalent systems. So this system is equivalent to this system, which is equivalent to this system, and it turns out that all of them have no solution. So let's look at another example. Let's say somebody gives you this system and asks you if the system is consistent. Now, one way that we can determine whether the system is consistent is just by trying to get a 1x in this position and a 1y in this position and a 1z in that position. If I call this equation 1 and this equation 2 and this equation 3, if I want a 1x, 1y, and 1z, and I don't want any entries over here, the first thing that I would do is I would use this x to get rid of that negative 4x. And I can do that pretty easily. In order to get rid of a negative 4x, I have to add 4 times x. So if I multiply equation 1 by 4, and then I add it to equation 3, well, that can be my new equation 3. And we'll have an equivalent system. So let's write all of that down. 4 times this equation gives me 4x minus 8y plus 4z equals 0. And then I'm just writing down equation 3 as is. When I add those together, the x's reduce, and I just have a negative 3y plus 13z equals negative 9. So now my new system comes from leaving the first and second equation alone. And replacing that third equation with negative 3y plus 13z equals negative 9. Now I'd really like to have no y's right here. Ideally, this would be completely gone. So one thing that I could do is I could multiply this by negative 1 to make that a positive 3. So we could take the new equation 3, equation 1 and equation 2 have been left alone. So this is our new equation 3, call it equation 3 star. I could take that and I could multiply it by negative 1. That would just change the signs on everything, right? I'll call that equation 3 star star. And equations 1 and 2, I'm still leaving those alone. And now with that, if I take equation 3 and replace it by equation 3 minus equation 2, then I will just have a 3y minus 2y is 1y. Oh, actually, I don't want a 1y right here. I want a 1y right there. I mean, I could get a 1y here, and that would make it easier. But ideally, I'd like to have a 1y right there. Well, that's okay. Let's talk about doing that. In order to make this a 1y, notice I've got a 2y, a negative 8z, and an 8. I could just divide that equation by 2. So multiply it by 1/2 and then make a replacement. So that's my new equation 2. And in order to get rid of this 3y right here, I could multiply this one by a negative 3, so that I have negative 3y plus 3y is 0y, and those would reduce. So we'll have negative 3 times the second equation plus the third equation. Of course, we're using the modified versions. It's going to give us negative 3y plus 12z equals negative 12. 3y minus 13z equals 9. And then we end up with negative z equals negative 3. And of course, we could multiply that by negative 1. So let's multiply that by negative 1, and we're going to call that our new equation 3. This is new equation 3. That's sort of the triple star. And then this will be sort of quadruple star. This is equation 3 triple star multiplied by negative 1. And so we end up here. We've got x minus 2y plus z equals 0, y minus 4y or 4z equals 4. And this last equation is just z equals 3. So when I have this matrix, or excuse me, this system of equations in this form, I know that I can solve this system of equations. I know that there's at least one solution, because this tells me that z equals 3. And if I know what z is, I can substitute that here and figure out what y is. And once I know what y and z are, I can substitute those up here and I can find out what x is. So it turns out that there's only one solution to this system of equations, and that means the system is consistent. Let's look at how that would evolve if we were looking at augmented matrices. So we start out here, and we want to list the coefficients here. I've got a 1, a negative 2, and a 1. and a 0 on the right-hand side. There's an implied 0 there. So we have a 0, a 2, and a -8, and then an 8 on the right-hand side, and then a -4, a 5, and a 9, and a -9 there. And then we said, I want to get rid of that -4, or I want to get rid of that -4x. So we took the first equation, we multiplied it by 4, we added it to equation 3 to get a new equation 3. That's the same as replacing equation 3, or replacing row 3 with row 3 plus 4 times row 1. So rather than writing all these plus signs and the x, y's, and z's and equals signs, we could just focus on the numbers because that's really all we're changing. We're going to leave the first row alone. We're going to leave the second row alone. But that third row we're going to replace with 4 times row 1 plus row 3. 4 times 1 is 4. 4 plus -4 is 0. 4 times -2 is -8. -8 plus 5 is -3. 4 times 1 is 4, and 4 plus 19, or plus 9, excuse me, is 13. And 4 times 0 is 0, and 0 plus -9 is -9. Notice that this, this row has the right coefficients that correspond to this. So this augmented matrix is the augmented matrix that goes with this linear system. So these are equivalent to each other. And then I said, for some reason, I wanted to make that a positive 3y because I was trying to get a 1y somehow. And so I was going to make that a 3y and then subtract the 2y, that row. But then I changed my mind later. That's okay. Before I knew any better, I decided I wanted to take that and multiply by -1, and that was fine. It was an unnecessary step, but it didn't hurt anybody. And I said, I really want that to be a 1y, and I noticed that all these numbers are divisible by 2. I've got a 2y minus an 8z and an 8. So I see a 2, a -8, and an 8 there. So what I decided to do is I'm going to take row 2 and replace it with 1/2 of row 2. Leave row 1 alone. Leave row 3 alone. Take each of these entries and multiply by 1/2. And then we're here. And then I said to myself, I really want to get rid of that 3. So let's replace row 3 with row 3 minus 3 times row 2. So we leave row 1 alone. We leave row 2 alone. And then we take this and multiply by -3 and add it to that. -3 times 0 plus 0 is 0. -3, or 1 times -3 is -3. -3 plus +3 is 3. -3 times -4 is +12. +12 plus -13 is -1. And then I've got -3 times 4 is -12, and -12 plus 3 is -3. And then I said, I really want that to be a positive z rather than a negative z. So let's replace row 3 with negative row 3. And we ended up right here. Notice that this augmented matrix corresponds to this system of equations over here. And then we just used reasoning. We said, if I know what z is, I can use z to find y. And if I know what y is, and I know what z is, I can use y and z to find x. So I know that this is a consistent system. I can look at this and tell that I have a consistent system in a similar way, because whenever I see this row, I'm really thinking of this equation. I'm thinking 0x plus 0y plus z equals 3. So this is telling me what z is. And once I know what z is, I can use this to get rid of that -4 times z from right there. And then I can find out what y is. And once I know what y is and I know what z is, I can use this 1y equals something to get rid of that -2y from right there. And I can replace that z with, well, 3 in this case, get rid of that 1 right there, and I can figure out what x is. So this form of the augmented matrix, where you have 3 zeros here, or zeros in this lower corner, and 1s along the diagonal that is corresponding to that coefficient matrix, and then just some numbers on the other side. If you see something like that, then you know, guess what? The system is consistent. It has at least one solution. And it turns out that solution is unique. Now, we have not proven that yet. I just told you it's a fact. You either have no solutions, one solutions, or infinitely many solutions. We're going to verify this fact in section 1.2.